Okay, it's 5:25, so let's get started. Just a few announcements. We've been having really good discussions about some of the course material and other things on Piazza. So if you haven't been participating on Piazza, first off, get on Piazza because it's part of your grade, and start participating on Piazza. So I've been putting out these daily exercises which may help you with clearing some doubts about the course material. I put one out yesterday, and we've had some really good discussions. So get on doing that. That's my recommendation. Problem set 0 is due on Wednesday. So who hasn't started it yet? Hopefully everyone started it. Okay. So are there any questions about problem set 0? Many.
Literally so many.
Ask him on Piazza. Are there any questions you want to ask right now? Yeah.
About the algorithm, pseudocode is fine?
Yeah, that's what I expect. Yeah. Pseudocode, yeah. As long as it's clear. Yeah. Any other questions about problem set 0? Okay, I expect a lot more on Wednesday then. Problem set 1 I'll put out tomorrow. It actually has some pretty interesting problems, so I hope you would like some of them. So the length of problem set 1 will be about problem set 0, if not a little longer, so be prepared for it. No recitations tomorrow because Independence Day. So enjoy family, enjoy your friends, hopefully not set things on fire, all that stuff. But recitations do start on Thursday, so the people who have their recitation section on Thursday, make sure to go to that. And then, so the way it's going to work is that the first recitation for Thursday will be this Thursday, and the first one for Tuesday will be next Tuesday. So, but it ends up being exactly the same number, 5 recitations each, so I think that's fair for everybody. And it's a little bit away, but it's going to come fairly fast. Midterm exam 1's on next Wednesday. And I'll give you some details as we get closer to that about how that's going to work. Any questions otherwise before we start? Okay, so what did we talk about last time? Yeah, these things called DFAs. And these things are called deterministic finite automata. And what we wanted was we wanted to model a really simple type of computer using this particular model. And so we wanted to be deterministic and to only have some kind of set of final states in which you say, okay, yeah, I'm going to accept this input or I'm not going to accept that input. Then we talked about what are called regular languages, which are the languages that are recognized by DFAs. Okay, so that's what they're defined to be, the languages that are recognized by DFAs. And so we came up with several examples. One example is that we had any string that's not the empty string, we had a DFA for that, and so therefore that language is regular. We had a DFA that accepted everything, and so that language is also regular. We had a DFA that accepted 0 strings at all, so the empty set, and so by definition that's also regular. So we can play this game of making some more DFAs and seeing maybe some interesting examples of regular languages. But I want to start thinking about how do we get some regular languages inform other regular languages from them. So today we're going to talk about operations on regular languages, or languages in general. So this doesn't necessarily apply to regular, but we're going to apply it to regular languages. Okay? So we're going to say, so this is a definition. So let C be a set of languages. So eventually C is going to represent the set of the regular languages. but this can be any set of languages. We say that C is closed under an operation, and I'm gonna, so this is called O plus. Can you tell why? O plus. So it's closed under an operation plus if this operation is applied to any language in C, the result is also in C. Okay? So I have this set of languages, and so I'm being deliberately informal here because I don't know for this O plus operation how many languages it's going to work with. Is it going to be a unary operation in the case of working with exactly one language, or is it a binary operation where it works with two languages, or whatever? So I was deliberately informal there. But the idea is if I apply it to some set of languages within C, the result language is also in C. Okay? So there's never a chance of applying to something in C and getting something outside of C. Okay? Cool. So with that in mind, we're going to talk about something called the regular operations. So you may think, well, this term regular operations, okay, that's probably going to mean, yeah, we're going to apply it to regular languages. Unfortunately, this field is full of terms that are used in different contexts. So regular in this setting actually means something else. But we are going to apply it to regular languages as well. So the regular operations there are three of them. The first one is union. So union here means if I have L1 and L2 are languages. So I didn't say that these were necessarily regular, but we're going to work with regular in a bit. If L1 and L2 are languages, then we're going to say L1 union L2. So union is this O plus operator, like we talked about. It's just the set of things X such that X is in L1 or X is in L2. Okay? So all it literally is just do union of two sets. Okay? Another operation is concatenation. So where have you seen concatenation before? I heard someone say strings. Right, so if I have two strings, if I want to concatenate them, I put one first, and then right after I put it on the other string. So we got to define this in terms of strings first, and then we'll define it in terms of languages. So if W and X are strings, where W is W1, W2, up to Wn, and X is X1, X2, and this may be a different length string, it may be the same length string. So let's say W is the string W1 through Wn, and X is X1 through Xm, so it's a different subscript there. Then we're going to write Wx, and this is sometimes written W with a little circle X. So we will commonly use drop the circle in between, but there actually is an operation happening there. And so this string, as you might expect, is W1, W2, up to Wn, and then the string X. X2, up to Xm. Okay? It's just what you've seen whenever you've been programming with strings. When you want to concatenate them together, say with plus, that's exactly what happens here. No difference. But then we got to define it for languages. So if we want to say that we have a language concatenated with another language, then take any element of the first language and concatenate it with any element of the second language. Okay? So we're going to define it for languages if L1 and L2 are languages, then L1, L2, and of course, it could be written with a circle in between to denote that an operation's there. Concatenation is just the concatenation of any two arbitrary strings in both languages. Okay, so I pick an arbitrary thing in L1, an arbitrary thing in L2, concatenate them together, and put it in this set. And then I do that for all pairs of strings in both languages. So just as a quick example, if we have L1 being 0 and 1, and L2 being X, Y, Z, then L1, L2 is, well, pick an arbitrary thing of L1, the language L1. Let's just pick 0 first, and concatenate it with any arbitrary element of L2. Let's just pick X. So I'm going to put 0x in my set. Then, as you might expect, 0y is in there, 0z is in there, as well as, well, I've exhausted all the possibilities for 0, so now I got to do the same thing for the other element in L1, which is 1. So we'll have 1x, 1y, 1z. Okay. Any questions on that one? Because this one throws people off sometimes. Yeah.
Maybe we're going to, is it similar to with like linear algebra where the order of the multiplication is the order of the L1, L2 will be the first, as in is OX equal to XO?
I'm not sure if it preserves the algebraic structure though. I'm not sure if it's a Boolean though. I'd have to check. Yeah, good question though. I don't know. Any other questions?
I think the question he was getting at is if it's L1, L2, could we swap those and the answer to that would be no.
No, so,
Oh, 0x is not equal.
Yeah, L2, L1 is different
oh,
than L1.
yeah.
Yes.
Yeah, so in general, L1, L2 is not equal to L2, L1. Yeah, that's correct. But obviously, L1 union L2 is the same thing as L2 union L1. Yeah. Yeah, that's an interesting question. I haven't thought of that. Any other questions about this? Okay, so this one is going to extend the notion of concatenation even more. So this one is called Kleene star, or just star. So I may drop Kleene there. Sorry, Kleene. So what this is going to be is, instead of working with two languages, we're going to work with one language, but instead of working with one concatenation where I pick two strings and concatenate them together, I'm going to pick an arbitrary set of strings. Okay? So what I'm going to have here is, if L is a language, then L superscript star, so we saw sigma star before, this is just extending that idea to any arbitrary language. Well, what do we want? Well, what we want here is that if I pick 0 things out of L, what is the resulting string that I have? Empty string. Yeah, so that's the thing that we want if we pick 0 things out. Well, if I pick one string out, concatenate it with itself, well, actually don't do any concatenations, what is the resulting language at that point? Pick any arbitrary string and stick it in. It's just L, isn't it? Yeah. So that's picking one element out of L and then putting it in the set that I want, in L star. Now I want to pick two things. So pick something out of L, then pick something out of L, any arbitrary element, concatenate them together, and put it in an L star. So how do I write picking two things out? LL, yep. So union LL, three things, LLL, and etc. Is this formal? It sure is not. How do I know where to stop? It seems like it goes on forever, but I may stop at some point. Well, let's make this more formal. More formally, L star is, well, I have a whole bunch of unions here. So I'm going to have union over k, any non-negative integer k, of union over L to the k. And of course, I haven't defined this L to the k thing, so I'm going to have it be L to the 0 is just the set which contains the empty string, so our base case. And L of k is L concatenated with L to the k minus 1 for k at least 1. Okay. So informally, what I want here is I want, so this set L star is going to have all strings that are a result of some number of concatenations of things from L. So it's extending our notion of concatenation to any number of concatenations that we want. So this is probably the one that trips people up the most. So let's do an example. So let's consider L to be, let's say, 0 and 1, 0. So a two-string set. So let's list off strings, let's say lexicographically. So what string do I know is an L star here? Empty strings always in the set L star. And then what other strings do we know are in there? Yeah, well, the things of picking exactly one thing from L, we'll just take the two strings and put them in L star, no problem. Now I got to pick two things out of L and concatenate them together. So what's an example string? 0, 0, right, because I picked, could I pick the same string twice here? Yeah, it's an arbitrary element each time. So 0, 0. And then, so that's with doing 0 both times. Maybe we want to do 0 first and then 1, 0 second, in which case we'll get the string 0, 1, 0. Then maybe we want to do 1, 0 first and then 0 second, in which case we'll have 1, 0, 0, and you get the idea. Okay? So it's just picking something out of L and concatenating it some number of times. Well, picking things out of L, any arbitrary elements, concatenating them all together, and then putting it in L star. Okay? Any questions about L star? Okay. Cool. So those are what are called the regular operations. We'll eventually see that the regular languages are closed under these operations, but we need some work to get to there. So I'll define one more operation. It's not under the list of regular operations, but it's another operation that we might consider. So it's called complement. So if sigma is the alphabet of language L, then I want the complement to be everything, every possible string, and take away the things in L. Okay, so if it's in L, it's not in the complement of L, and if it's in the complement of L, I don't want it to be in L. Okay, so it's just like complements of sets, but just generalized to sets of strings here. So then we're going to denote L bar, so the bar is on top, which represents complement. We're going to define to be sigma star without L. Okay? Yeah, go ahead.
Is this the same complement that in your textbook it reduces it to C?
So there are other there are other ways of writing it. So like in the problem set 0, I have the complements of strings, which is not the same thing as this, but I raise it to a power C. Here I've seen the notation L to the C before. It means exactly the same thing. Yeah, but the notation we'll use is L with a little bar over it. Any other questions about complement? Okay. So what do we got to do next? Well, let's actually try to prove a result, our first result in the class, which is the thing I said before, that the set of regular languages are closed under complement. So in informal terms, what does this actually mean? What am I trying to prove? Yeah.
You're saying that the complement of L is only references those elements that are in the complement of L.
No, in the theorem, I'm saying.
Oh,
In the statement of the theorem. It says, if I take an element out of this set of languages, then I apply the operation to it, then the result must be also in that set of languages. So the set of languages here is the regular languages, and I'm saying if I apply complement to a language in this set of regular languages, I also get a regular language. Okay? So what this is saying is that if L is regular, then L bar is regular. Okay? So that's the thing that we're going to try to prove. So, proof. So let's say that we have this language L, and I know it's regular right off the bat. What can you immediately tell me? It has a DFA for it, right? That's the definition of it being a regular language. We'll see other equivalent forms of regular languages eventually, but the only one that we know right now is that that there is a DFA for it. So, since L is regular, there is a DFA. I'm going to call it M, with states Q, sigma as the alphabet, delta, transition function, Q0 start state, F set of final states. There is a DFA recognizing L. Yeah, that's the definition of L being regular. There is some DFA. I don't know anything about the structure of this DFA, but I know that there is one. Okay, so I can call it states Q, alphabet sigma, transition function delta, Q0 start state, F set of final states. But I don't know anything about the structure of the DFA right now. Well, if I want to prove to you that L bar is also regular, how do I do that? I produce DFA for it. Okay, well, maybe I can use this DFA M to help me here. So if I can produce a DFA that I know has language L bar, I've proved the result. Okay? Well, let's see. What is the language of M? Well, we defined it last time as the things in sigma star such that M has an accepting computation on W. Or you can phrase this another way. The only computation of M on W is accepting. So we'll do that. So another way of saying this is same thing. The only, so that word only will be important in a second. Computation of M on W is accepting. Well, let's see. By the definition of complement, if this particular string W is in the language of M, is it in the language of the complement? No, because we defined complement as being the set of strings in sigma star that are not in L. Okay, well, let's see. So if W is in L, it's not in the complement. And we also know if W is not in L, is it in the complement? Yeah, that's the definition of complement again. Well, let's see. Could I modify this DFA in such a way that I get exactly L bar? Well, let's see. How do I accept W? Or how does M accept W? How do I know that an accepting computation happened? It ended in a final state. Well, if I wanted to make a DFA for L bar, what better it end in? In a non-final state. Should I change the transitions at all? No, because I don't know the structure of the DFA here. So what do you think I could do to my DFA M here? Oh, switch the final and non-final states. So if it was final before, it's not final anymore. And if it's not final before, it is final now. Oh, well, we have the description of M right here. What is the only thing that I need to change? The set of final states, right? I don't need to change the set of states, alphabet, transition function, or start state. So how do I represent all states in Q, but not in F? Well, we haven't defined it for a set of states, though. But they are sets. Do I have a way of taking elements from a set from another set? Yeah, what's that operation called? Yeah, set minus. And there are two notations, Q minus F or Q minus F. So let's make a DFA. M bar. So this is just a name. The bar on the M here means absolutely nothing. It's just to indicate to us that it represents L bar. So I'm not going to change the states, alphabet, transition function, start state, but I am going to change the final states. Okay? So I claim that the language of M bar is L bar. So the language of this DFA that I just produced actually is the complement of the original DFA. Why is that?
Because the accepting states are disjoint.
That is true, but there's something really important about running a particular string on the machine. How many computations are there of M on W? Exactly one. There's only one computation. There can't be two, there cannot be zero. So we know that no matter what we do, it'll do the exact same computation every single time. So it'll land in the same state every single time. So Rn, like we defined last time, is exactly the same every time. So Rn is either an F or it isn't. So if it is an F, this thing says that now it's not an F. And if it wasn't an F before, it now is, because I flipped what is final and not final. But since I didn't change any of the transitions, I must do the same sequence of states as I did before. So whether I accepted before, I do the exact opposite now. So I must have the complement. Okay? So the proof of this is that there is only one computation of M on W. I shouldn't say only, I should say exactly, to be more precise. Okay? So we have proved, now our first proof, that the regular languages are closer to complement. So no matter what DFA I have, whatever language it has, its complement is also regular, which is kind of nice. So, for example, if we had a DFA that looks like this, okay. So I don't know what language this is, okay, because I just made it up. I really did just make it up. But if we say that this thing has language L, how do I get a DFA for language L bar? Oh, a DFA for it. Yeah, so just make a literal copy of the DFA and change what was final to be the opposite of whatever it was. So I'm going to have my three states as before, same transitions, because we didn't modify the transitions at all. Same start state. But since the state on the right was final before, I'm going to make it non-final now. And the other two states were non-final before, so now they are final. Okay? Any questions? Sweet. Yeah, go ahead.
Would it mean anything in particular if the start state is the final state? Like, would it mess up the, or does it just mean it can end at that state?
Okay, so yeah, that's a good point. So the question was raised that now the start state is final. Does that mess up the language of the DFA now? No, why? How do I know that I'm done computing with a string? There's no more input. Well, if I'm at the start state and the input has some characters in it, am I done with the computation? No. Yeah. But if I happen to have the empty string, then I already ran out of input, so I stop at the start state. So whatever language L bar is here, it has the empty string in it, because we know that the start state is final. Any other questions about this? Yeah.
So there's only one computation for both M and M bar?
Yeah. So because it's a DFA, it's completely deterministic. So there's exactly one transition to do at all times, and I must do that transition. So there's exactly one computation on any input. Yes. And so that was how we were able to prove that by flipping the states, we can get exactly one computation. So I landed in the same state, and because I changed what was final and non-final, the result of whether it accepted or not flipped for every string. So I get the complement. Any other questions? All right, let's prove some other stuff. Well, if we come back to our list of, all the way up here, list of regular operations, well, the first one, we haven't proved any of the three, union, concatenation, or star, for regular languages. So let's just start at the top and work our way down. When we hit the second one, that's going to cause us trouble. But when we get to the first one, let's see what happens. So let's talk about union of regular languages. So our question is, if L1, L2 are regular languages, is L1 union L2 regular? If we can answer this in the affirmative, then we have proved that the set of regular languages are closed under union, which is what we wanted to set out to do anyway. Well, suppose I tried to do this. So if I assume that L1 and L2 are both regular, what does that immediately tell you? There are DFAs for both. So let's just try to do this. So I have a DFA for both L1 and L2. So I'm going to get some input. So what I'm going to do is I'm going to feed it through the first machine, let's call it M1, feed it through M1. Then if it accepts it, then I say, yeah, it's in the union. But if it doesn't accept it, then I'm going to rewind the tape or rewind the input, feed it through M2, and see if it accepts, and then put it in the union whether or not it accepts. Would that idea work? I don't think so. Yeah. For DFAs, we don't have this operation of going back and looking at what we've already read before. So that seems kind of an issue, right? If I know that there are two DFAs for L1 and L2, then how am I going to work with both machines at the exact same time? That seems problematic, right? So let's work with an example, and then we'll see how to generalize it. So let's say I have these two DFAs. They're really simple DFAs. So I'm going to call this guy M1, and I'm going to call the second guy M2. The hardest part about this class is coming up with examples. All right, so I have two two-state DFAs over the same alphabet, 0, 1. And the states of the first are Q0, Q1, and the states of the second are R0 and R1. So let's look at the string 0, 1, I'll make it a little bigger, 1, 1, 0. So maybe what I could do is, since I can't run one machine and then run another, what would a better idea might be? I can't run them sequentially. What could I do instead? Maybe a parallel. Maybe I can try doing that. Let's see what happens. So at the very beginning, before I read anything, if I look at what I'm going to do in both DFAs, what state am I in both DFAs? Q0 in the first guy, R0 in the second. So I'm in Q0 in the first, Q1 in the second. Oh, not Q1. R0. Okay, well, now let's trace the computation in parallel. So if I read a 0 in the first DFA, where do I go? To Q1. All right. I'm in R0 and I read a 0, where do I go? R0. So this seems pretty simple. If I'm in Q1 and I read a 1, where do I go? Q1. And actually, the rest of the first row is going to be easy because it's always going to be Q1 in this particular case. Okay? Second row. If I'm in R0 and I see a 1, where do I go? R1. R1 and I see a 1, where do I go? R0. R0 and I see a 0, R0 again. Okay. Well, let's see. Let's consider union here. Would I accept 0110? Is 0110 in the union of these two languages, whatever they are? Yeah, how do you know? Yeah, Q1 is a final state. Because we ran out of input. Does it matter that R0 is not a final state? No, because I only need one of them to end up in a final state. Maybe both could have been a final state. If I made R0 final as well, then when I ended up in here, Q1's final and R0's final. But as long as at least one of them's final, then I'm all good. Okay? Well, let's see. Could I possibly, maybe not in this example, but could I possibly visit all pairs of states? So if I see Q0, R0, Q1, R0, Q1, R1, so I see 3 of the 4 combinations, but could I see all pairs possibly? Not with these two, but in general. Could I see all pairs? Maybe. Okay. Well, and how did we know what to do when we are in a pair of states, Q0, R, whatever? When I saw the next input character, I looked in the first DFA and I saw where would it have gone on that particular character? Then I figured out where it went. Then I looked and said, okay, if I'm in R0 and I see a 0, where am I going to go here? Okay? And how do we know what is a final state or not? Well, or how do we accept an input? Well, we look at wherever we ended up and we say, okay, if either one of these guys or both is a final state in the original DFAs, then I'm going to say, yeah, I accept that input because it's the union of the two languages. Everyone following? Anyone have questions? Okay, so let's generalize. So, theorem. Regular languages are closed under union. Proof. Well, what I need to do is I need to take any two arbitrary regular languages and show that their union is also regular. So let L1, L2 be any regular languages. I know you're going to get sick of this question, but I'm going to ask it over and over. L1 and L2 are regular. What does that imply? They have DFAs. Thank you. That's like music to my ears. All right. So therefore, there is a DFA M1, and I'm going to give the 5 pieces, but with a subscript 1 on them to denote that it's M1. So Q1, and to make things easier, and I claim it doesn't change the result, I'm going to make the alphabets the same in both DFAs. Delta 1, Q01, F1 for L1, and there's also a DFA M2 with possibly other states, same input alphabet, but maybe transition functions different, maybe start states different, maybe final states are different for L2. Well, let's see. Do I know the structure of these two DFAs, M1 and M2? Nope, they're arbitrary DFAs. I know they're DFAs, but I don't know anything else other than that. So if I pick some, do you have a question? Oh, that's my error. So I like putting the little pointy things to make it look like sigma instead of the empty string. Yeah. Yeah. So should you type your assignment or should you handwrite it? Thank you. All right. Well, since I don't know the structure of this, if I pick some arbitrary string and feed it in parallel like we did before to both of these DFAs, could I visit all possible pairs of states from Q1 and Q2? I might. I don't know. But do I lose anything in looking at all of them at the same time? No, I don't lose anything. Why? Because all I need to show you is that the number of states is finite. So a finite number of states in Q1 times a finite number of states in Q2, is that also a finite number? I better hope it is. So we're gonna construct a DFA. I'm gonna call it M. So I'm gonna drop the subscripts. As follows. So what I have to do is I gotta define all 5 of those pieces in terms of the original 2 DFAs. Okay, so this first one, Q, well, what we could do is, well, we could analyze the structure of the DFA and say, okay, maybe we don't need this pair of states, but I don't know that here. So let's keep track of all ordered pairs of states. So all possible states in Q1 paired with any state in Q2, and keep all ordered pairs. Well, how do I write the set of all ordered pairs involving Q1 and Q2? Exactly. It's Q1 cross Q2. Cartesian product of the 2 sets. Okay? Well, I think the alphabet's pretty easy. I hope. So I'm going to skip that one because it's the same. Well, I'm going to skip to the last 2 coordinates first. So I'm going to do the start state, then final state, then we'll do the transition function. So Q0 is, well, so I'm going to ask this question several times. What are states in this machine M that I'm making? They're ordered pairs of states. They're Cartesian pairs, right? So Q0 better be an ordered pair, right? Because it's a state of this machine M. So I got to make a ordered pair there. So I'll get there. Well, I got to put something involving Q1 in the first coordinate, and then something involving Q2 in the second coordinate. Well, what thing should I put in both of those? The start states in both of them. Oh, we have the descriptions of the machines available to us, so let's use them. So the start state in the first guy was Q01, and the start state in the second machine was Q02. Super. Actually, I'll do F last. And you'll see why in a second. So let's see. I gotta define the transition function of this machine M. What are states in M? Ordered pairs of states. So what does the transition function of a DFA in general take as input? Takes two things, a state and a input symbol. Okay, well, since it takes a state as the first thing, what should I put in the first coordinate? An ordered pair, because it's a state. So let's say that the ordered pair is Q1, Q2. And let's say in general that the symbol is A. So I'm in this state Q1, Q2, an ordered pair, but it's a single state of M, and I'm reading the symbol A. And now I got to figure out what other state do I need to go to. So the transition function outputs a what? State. What are states in this machine? Ordered pairs. So I think I better write an ordered pair. It's going to be a long ordered pair. Well, so let's look at the example that we did before. How did I know that in Q0 we went to Q1 when reading a 0? Oh, we looked at the transition function of that particular machine and we just saw what it did on that particular input. And how did we know to get from R0 to R0? Same thing, but for the second machine. So let's do that here. So the first coordinate better be a state of the first machine. So what thing am I going to look in to find out what I was supposed to do? Delta 1. Yeah, because that's the transition function of the first machine that'll tell me what state I was supposed to go to. So I'm going to look in delta 1. Well, it takes a state of Q1 with a symbol. What state of Q1? Capital Q1, I mean. Well, what state of the first machine am I currently thinking I'm in right now? Little Q1, yeah. So I better figure out what this transition function on Q1A is supposed to do. And that's exactly what we did in our example. We looked at the first transition function and said, I'm in this state and I'm reading this symbol. Where am I supposed to go? And we saw what we did for the first machine. What did we do next? Same thing for the second machine. So what do you think is going to go in the second coordinate? Delta 2, Q2A. That's just formalizing the exact notion that we did before. So what I'm going to do is whatever pair I'm in, whatever symbol I'm reading, I figure out what the first machine does, put it in the first coordinate, then I figure out what the second machine does, put it in the second. Yeah. Yeah, so great point. So I'm assuming that the alphabets are the same here. If they are different, then a common way to fix this is to union the two alphabets. But the problem might be that if they're different, then each of the DFAs is going to have an undefined transition. And then we wouldn't know what to do. So then we would need to use NFAs, but we haven't talked about those yet. So yeah, so it's just making the proof a little simpler by making the alphabets the same. Any other questions? There is a way to fix it though, otherwise. Yeah. Yeah. I haven't talked about that yet. Yeah, hopefully after the break. Any other questions about this? What piece haven't I defined yet? Final states. Let me ask you something really important that's actually pretty cool. Have the pieces that I've defined have anything to do with union? No. When we looked at our example before, How did we know whether to accept or not? Looked at the final state at the end. Oh, so that's the only thing that involves that is the set of final states. So all 4 other pieces have nothing to do with union. So the only thing that has anything to do with union is this last piece, the final states. So now we got to figure out what F is. What is final states in general, the structure of it? It is a set. So I better write a set. If I don't, then we're in bad shape. All right, well, if F is a set, it's a set of states. What are states in this machine? Ordered pairs. So I better write an ordered pair. So I'm going to write ordered pair Q1, Q2. So little q1 is in a state in the first machine. Little q2 is a state in the second machine. So how do I figure out whether or not this ordered pair is a final state or not? Yeah, so either q1 is in what? The final states of the first machine. Oh, what is the set of final states in the first machine? F1. So either Q1 is in F1 or Q2 is in F2. Could I have both? Or both. So this or both at the end is not necessary to write, but it's some people have trouble with either or, meaning that you could have both, so I explicitly put it there. Okay? Cool. Any questions about that? What if I wanted instead to do intersection of the languages instead of union? Yeah, so what would I need to change here? And I'm going to use a different color for that. Use and instead. So I'm going to put and here, and then strike out or both. And this is for intersection. Everything else stays the same because it had nothing to do with union. Cool. So what did we just prove? We actually proved 2 things. Well, we haven't really proved it, but regular languages are closed under union and intersection. Because there is a way to get it here. Because all I need to do is just make both coordinates final states in the original 2 machines. So I'll introduce you one more before we take a 5-minute break. Something called symmetric difference. And this is the set W such that W belongs to L1 or W belongs to L2, but not both. So instead of union where I could have both of them, intersection where I must have both of them, symmetric difference is exactly one of the 2 sets. And I can't have both and I can't have neither here. What did we just prove about symmetric difference? Or implicitly prove? Look at our construction. Did the first 4 pieces have anything to do with symmetric difference? No. So the only thing we needed to change was the set of final states. Could I make the set of final states here for symmetric difference? Yeah. How do I do it? Yeah, so here I would have, I would have Q1, Q2, such that Q1 is an F1, or Q2 and F2, but not both. and everything works exactly the same. So just this one construction called the product construction, this one construction actually can give us a lot of things that we know that regular languages are closed under. So if you wanted to get intersection of the languages of two DFAs, done. Union, done. Symmetric difference, also done. Set minus, also done. Because if we have set minus, that is just L2 minus L1, let's say. But that just means everything in L2, take away L1. So that's just the things in L2 and not in L1. Do we have closure under complement? Yep, we proved it earlier. Do we have closure under intersection? Yes. So we have set minus 2. And so this lets us get into a whole set of possible things that regular languages are closed under. Any questions about this? So let's take a 5-minute break.